Today's video will focus on electrode potentials, and like my other videos, I will go through a few questions on electrode potentials. A key topic: last year the examiner's report for AQA stated that nationally this topic was the most challenging topic and overall not well done by majority of students. This comes under redox equilibria. In order to understand this topic, it's really important to revisit the redox topic that was done in year 12. And the key thing to note, and if I do a bit of a summary of what this topic is about, it's about a chemical reaction that generates energy or generates electricity. That's what it is. Redox reactions involve electron transfer, and an electrochemical cell uses electron transfer reactions to produce electrical energy. Most batteries, laptop batteries, mobile phone batteries, they all work on this concept. And the easiest way to understand this is I'm going to use this little bit of space to explain this. We have two half cells. So we're going to do a copper and zinc half cell. Copper is the positive end, zinc is the negative end. Going to connect this with a high resistance voltmeter, and then we're going to connect this with a salt bridge. Okay, so I'm not teaching the topic. The idea is to just cover a few questions. Then you've got your electrolytes, zinc sulfate and copper sulfate solution. Your salt bridge completes the circuit. Your high resistance voltmeter ensures no external current is flowing, and the electrons will flow from zinc to copper. Copper is the right hand side, so that's where reduction happens, and left hand side is where oxidation happens. Copper is the most positive side and zinc is the negative side, and the overall cell potential can be worked out by right hand side minus left hand side, or the electrode potential of most positive take away least positive or most negative. If you understand what I've just done, that's the whole topic. The concept is on that. So copper 2 plus reacts with zinc to produce zinc 2 plus and copper. Copper 2 plus is reduction, remember, because reduction happens on the right hand side, and zinc is getting oxidized. Zinc is your reducing agent. It reduces copper 2 to copper. Itself, it gets oxidized. And then if you were to do a cell convention, a double line to show you your salt bridge, a solid line to separate your physical states, that now is your cell convention of the reaction that's happening. Right hand side, left hand side, and that's it. Now the types of batteries we deal with, or the types of cells we deal with non-rechargeable, rechargeable and fuel cells. So this first question that we're going to look at now is from the 2025 paper, and the idea is to look at a few questions and few things you need to learn. So give a half equation for the reaction occurring in alkaline conditions at the electrode, at negative electrode. You just got to remember these reactions. It's a question of memorizing these reactions. Hydrogen is a positive ion, so it goes to the negative. Reacts with hydroxide, produces water and electron. And then at the positive, oxygen is a negative ion, so goes to the positive, reacts with water and 4 electrons and produces 4 hydroxide. Note something important. One half cell will have electrons on the right, the other half cell will have electrons on the left. When you add the two half cells together, you get an overall equation where water is produced. Whether you have an acid, the hydrogen fuel cell under acid conditions, or the hydrogen fuel cell under hydroxide conditions, both will produce water as your product. So, and the hydroxide ions that are produced in one half equation will be used in the other half equation. So that basically is the reaction that is occurring. And it says describe how reactions at the electrodes generate an electric current that can power the motor in the external circuit. Basically, remember, electrons released at negative electrode flow to positive. So it's the movement of electrons that powers or generates electricity in that sense. So that's the reaction that's happening. And this part D, it says the fuel cell uses pure oxygen. So remember what a fuel cell is. A fuel cell needs a fuel, hydrogen or ethanol, and it needs an oxidant, which is oxygen. That's simply what a fuel cell is. So the gas that reacts, the gas in the air that reacts with hydroxide is carbon dioxide, because carbon dioxide is an acidic gas. Okay, now I'm going to skip a few questions. I'm not looking at every single question here. What I'm really looking at is some key questions that repeat themselves many times. When you've got a hydrogen fuel cell, the overall cell reaction is the same, because whether you've got acidic the fuel cell under acidic conditions or the fuel cell under alkaline conditions, the product will be water. Okay, now question 2, second question. Let's look at this figure. Okay, now you've got to be able to draw these. This is your hydrogen fuel cell. This is your hydrogen half cell on one side. It needs hydrogen at 100 kilopascals and 25 degrees Celsius and 1 molar concentration of hydrogen ions. So this is a mistake. You either have 0.5 molar sulfuric acid or 1 molar hydrochloric acid here. The other mistake here, which you can see, is this one. The electrode must be platinum. So where you have two solutions in the other half cell, then your electrode should be platinum. And the salt bridge should be soaked in potassium nitrate solution in here. Okay, so those are some of the mistakes. Now, voltmeter has to be a high resistance voltmeter, and what I want to talk about now is the electrochemical series in front of you. This is the most positive, this is the most negative. So when connecting two half cells, you always reverse the negative one. So let's see, we want to look at a reaction here. Let's look at the question. The finely powdered iron filings are added to copper sulfate. So we're looking at this half cell and we're looking at this half cell. Okay. Now, why does this, let's now look at why this reaction will occur. This reaction will occur because iron can react with copper 2 plus because the Fe2 plus Fe half cell electrode potential value is more negative than the half cell value for copper. So iron will reduce copper. That we know. Iron will react with copper. And that's an important reaction we are looking at here. Now let's look at the question in front of you. The solution changes from blue to pale green and brown. In other words, it's going from copper 2 plus to copper. Use the data in the table above to explain these observations. Give an ionic equation for the reaction occurring in this case. Okay. So what's happening here is the following. Your copper is a brown solid. Okay. Fe2 plus is green because, or pale green, because we know that from our knowledge of transition metals. And the reaction is occurring because, as I said, the electrode potential value for the Fe2 plus Fe is more negative than the electrode potential value for copper 2 and copper. In other words, the electrode potential value for the overall cell is right hand side minus left hand side. Copper is 0.34 and iron is minus 0.44, and that gets you the reaction overall. And what's the overall equation? Let's go back here. Copper 2 plus, iron 1 will be reversed. So let me just rub out a few things. So the reaction that occurs is Fe reacts with copper 2 plus to form Fe2 plus and copper, and you can see the reaction that is being reversed. And that's really it for an understanding of this topic. Let's look at question 3 as well. Now question 3 is from a different year. I think it's from 2023. Okay. Again, let's look at the data in front of us first. You've got magnesium is a powerful reducing agent because to the right of the arrow are your reducing agents and to the left of your arrow are your oxidizing agents. Oxygen is a powerful oxidizing agent because it's the most positive. Magnesium is a strong reducing agent because it is most negative. Question part A states that use the data in the table to explain why zinc reduces an aqueous solution of VO2 plus to V2. In other words, why can zinc reduce VO2 to VO? Let's look at the oxidation states here. Let's enlarge this. The oxidation state here is plus 5, plus 4, and then plus 4 can be reduced to plus 3, and plus 3 can be reduced to plus 2, all by zinc. Because zinc is more negative than all of these 3 values we're looking at. So just as we answered the question above between iron and copper, use the data to explain why zinc reduces it, because for each reaction, if we look at it, when zinc reacts with the first reaction, your electrode potential value is 1 minus 0.76. So for those two half cells, plus 1.76. For the next half cell, 0.34 minus minus 0.76. So I'll just double check. So you can see there that again that is positive, and that will give you an answer of plus 1.10. And then for the last one, minus 0.26 minus minus 0.76, I believe that comes to plus 0.5 volts. So you can see now that the reaction is the same sort of question is being asked here. Okay, then C says two half cells Fe2 plus and iron and VO2 plus V are connected. Calculate the EMF of the cell. Fe2 plus to Fe has a value of minus 0.44 and VO2 to VO3 has a value of plus 0.34. So the electrode potential value will be more positive minus least positive, and that comes to plus 0.78 volts. Give the conventional representation. Now the way we do the conventional representation, more negative one is on the left hand side. Shall we give state symbols? Not a bad idea. And then VO2 plus. So the species with the highest oxidation state are on either side of the salt bridge. That's aqueous, a comma because H plus is aqueous, a comma because V3 plus is aqueous, and then platinum as your solid. Remember, where you got aqueous solutions in the second half cell, we will use platinum as our electrode. And then the half equation for the reaction that occurs at the negative electrode, well, iron is more negative. So let me just show you. Iron is more negative in this half cell. So that's the reaction we will reverse, and that gets you Fe 2 plus and 2 electrons. And that really is the topic. And people find this topic quite challenging. Just to finish off, let's look at one more question here, which hopefully will help us to understand. Actually, one other thing I just want to cover, and that's this question here. Commercial electrochemical cells can be rechargeable and can be non-rechargeable. State why lithium cells can be recharged. The answer is that the electrode reaction can be reversed. But this is the reaction I think you need to learn. For lithium half cell, just learn this reaction. There's no mention of it that you have to learn it in the specification, but there's been a few questions that have come up on this topic to do with lithium, so my advice is just to learn that. Right, let me finish with this question 5. The question is about cells. The half reactions are shown. There's your negative, there's your positive. By convention, half cells are also always written in the negative. So when we combine these, then remember, zinc reaction will reverse if we combine these. Identify the oxidizing agent in this species. Well, there's your oxidizing agent because zinc is your reducing agent. So MnO2 is your oxidizing agent. State the function of the porous separator. That's acting like a salt bridge. So it's completing your circuit. Then give an equation for the overall reaction. That's negative. So that's negative. And that's positive. Okay, when it's recharging, that's the key, very important. Look, the reaction happens like this. Zinc reacts with Ag2O. Okay, I think the waters will cancel, and it produces 2Ag and zinc oxide. That's the reaction when the cell is being used. The question says when it's recharging. When it's recharging, you are reversing the reaction. It's very easy to lose a sight of that and very easy to make that mistake. And then the rest, hopefully, we have covered before. So that basically is the end of this topic on electrode potentials. It's not a hard topic, but the key thing to note here is that it's worth 15 to 20 marks. So I will